Welcome back. This is our fifth part of photosynthesis. Last time we talked about how the light reactions are used to synthesize ATP and NADPH, and both of those are required for the synthesis of sugars during the Calvin cycle. So don't forget, the overall goal, the purpose, the function of photosynthesis is to make sugars, and the light reactions are a means to the end of doing that. The light reactions make the molecules needed to take the carbon dioxide from the atmosphere and convert that carbon dioxide into sugars that the plant cells can use, and ultimately then that you can use when you consume plants and animals that in turn consume plants. So let's take a look at the Calvin cycle, and this looks complicated, it looks confusing, but we can break it down and that'll make it a lot more digestible. So this is pretty much all we're going to look at in this session. Let's go back to the structure of the chloroplast up here in the top left. We talked about the light reactions that occur over here on the thylakoid membranes, and we oxidized water to produce oxygen and used those electrons ultimately to create a proton gradient that made us capable to produce ATP and NADPH. So the Calvin cycle is going to work in the stroma of the chloroplast. That means the ATP and NADPH that are made by the light reactions must be made in the stroma, and that's important. That's why you have ATP synthase oriented the way you do in the membrane. That's why you have NADP reductase on the outside of the thylakoid membrane, so that when these molecules are made, they're made in the stroma and they can be used by the Calvin cycle. Calvin cycle breaks down into three sections. The first one up here at the top is going to be phase 1, and then we'll look at phase 2 next, and then we'll look at phase 3, and as we do that we will introduce the specific names. So let's go back to the top up here, and we're starting up here in this top triangle. I'll try and trace it so you can see what we're looking at. So we're dealing with the processes up here in phase 1, and this is called carbon fixation. This is where part of the Calvin cycle is going to take some carbon dioxide molecules and combine them with some molecules already in the Calvin cycle, and that is the fixation of a gas onto a solid, so that the carbon dioxide is converted into a solid form. It is fixed from a gaseous form into a solid form of matter. So that is a matter transformation, if you like. Okay, so what's going to happen is we're going to take 6 molecules of carbon dioxide. Now, there are different ways you can look at the Calvin cycle. This is but one way. We're going to look at 6 carbon dioxides coming into the Calvin cycle, and so what we're going to do is we're going to take each of those carbon dioxides and we're going to add them to a molecule called ribulose bisphosphate, which is down here, abbreviated RUBP, and RUBP has 1, 2, 3, 4, 5. So if we take 6 of these 5 carbon ribulose bisphosphates, and to each of those molecules we add a carbon from carbon dioxide, we go from 6 5-carbon compounds up to 6 6-carbon compounds. That's because you start off with 6 5-carbon compounds. There's 1, 2, 3, 4, 5, 6 of those, and then to each of those you add another carbon, and so now we've got 1, 2, 3, 4, 5, 6 carbon compounds. They are unstable and they immediately split, each one in 2. So we go from 6 6-carbon compounds to 12 3-carbon compounds, and those are called phosphoglycerate, and that's what this is here. Okay, what is critically important here is that you track the carbon. You've got to keep track of the carbon. So we start off with 6 times 5, so 5, 10, 15, 20, 25, 30 carbons to start with, and now we add in another 6. 30 plus 6, we're up to 36 at this point. We rearrange those by splitting some of them up, or all of them up, and we end up with 12 3-carbon compounds, and so that is 12 times 3 is 36. So at the end of this first stage of carbon fixation, we end up with 12 3-carbon phosphoglycerate molecules. You don't need to worry too much about the names of these things, but you do need to keep track of the carbon. That will become important to understand the Calvin cycle. Okay, so that is the end of carbon fixation. That step is catalyzed by an enzyme called rubisco, which stands for ribulose bisphosphate carboxylase oxygenase. Really complicated. We call it rubisco. It is the most abundant enzyme on the planet, and has its critical role in fixing carbon dioxide into a solid form of matter. So at the end of carbon fixation we go into our next stage, which is kind of this dark green shape here. So what's going to happen in here is phase 2. That's called reduction and sugar or carbohydrate production. I call it the reduction stage. We take those 12 3-carbon phosphoglycerates that we produced in the carbon fixation stage, which are right here, and each one of those is going to undergo some reactions with ATP. So each of these 12 molecules needs 1 ATP and 1 NADPH. Remember, we got those from the light reactions. This is where we're going to use some of our ATP and all of our NADPH from the light reactions. So you take 1 3-carbon phosphoglycerate, an ATP and an NADPH. You do all the chemistry. You use the NADPH with its electrons from the light reactions to reduce the carbon that you just added in carbon fixation. So you're taking electrons from NADPH and you're giving them to the carbon you just added. Now when you add electrons, you're often adding hydrogen, so we're going to be introducing hydrogen as well here. So if you put in 12 3-phosphoglycerates, then you're going to need 12 ATP and you're going to need 12 NADPH. So out of this, you're going to get 12 molecules called glyceraldehyde 3-phosphate. Now if you looked carefully at glycolysis, you saw that was an important intermediate in glycolysis. That was one of the molecules that you got from the breakdown of sugar in glycolysis, the breakdown of glucose. So we'll look at that in a moment. We're going to get those 12 glyceraldehyde 3-phosphates, we call them G3P, and we're going to get 12 ADP out, because if we use an ATP up, we get an ADP out, and we get 12 NADP plus. Now where do they go? They go back to the light reactions. Let's go back up to our chloroplast. So the NADP and the ADP that we get out of the Calvin cycle get fed back into the light reactions here, so that we can make more ATP and NADPH for the Calvin cycle. So it's all cyclical. There's no waste here. What we use up, we put back into another cycle to regenerate what we need. So at the end of the reduction stage, we've got these 12 G3Ps. That's 12 3-carbon compounds, but what we've done is we've reduced the carbon that we brought in from carbon dioxide. We've given it electrons. Like you see in glucose, the carbon is reduced. So what we're going to do now is we're going to take those 12 G3Ps and we're going to take 2 out of the cycle. So 2 get pulled out of the cycle. So that's 2 G3Ps, 3 carbons each, 6 carbons get pulled out. So we're back down to 10 G3Ps going into the next stage. Okay, before we get to the next stage, let's look at these G3Ps which get pulled out. So these 2 G3Ps down here that get pulled out, they get used to make glucose and other sugars. Now this makes sense, because if you take a sugar and you make glyceraldehyde 3-phosphate in glycolysis, you stick them back together again and you can make glucose. So that's how we make the sugars. We don't actually get glucose out of the Calvin cycle. We get those G3Ps which can then be built back into sugars like glucose. So we've taken 2 of those out, so that means we've only got 10 G3P right here going back into, or continuing through the cycle. And so now we're into the last phase of the cycle, and this is called the regeneration phase, this last stage down here. So what we're going to do is take those 10 3-carbon compounds, so remember, 10 3-carbon compounds, so back down to 30 carbons, because we took 6 out when we took 2 3-carbon G3Ps out. So we've got 30 carbons. So what we're going to use now is some ADP and ATP. So we're going to use some ATP from the light reactions, and we're going to shuffle all the carbons back round and go from 10 times 3 G3Ps, we're going to go back to 6 5-carbon ribulose bisphosphates, and so we end up back here where we started from, and that's called regeneration, because we're just regenerating the RUBP. And then we can do another round where we put in more carbon dioxide from the atmosphere, and we need more ATP and more NADPH. So the whole point of this is to put in 6 carbon dioxides and pull out 6 reduced carbons. And so here you're seeing the oxidized carbon dioxide going at the bottom and the reduced carbon coming out in the form of G3P at the bottom. Okay, so those are the 3 stages of RUBP, of the Calvin cycle. You don't need to really memorize all of these names, but it helps. You definitely don't need to worry about memorizing the structures here. Okay, the last thing we're going to look at here is the ratio between ATP and NADPH. So take a look at this real quick. You need 12 plus 6 ATP, that's 18 ATP to do 1 turn of the cycle, and you need 12 NADPH. So let's finish up with this question that'll help you think about the ratio between those two. Okay, so is what we have 12 plus 6 ATP. That's 18 ATP are needed, but only 12 NADPH, and that gives us 1 turn of the cycle. So 18 is 50% more than 12. 12 times 1.5 is 18. So you need 50% more ATP to drive the Calvin cycle than you do an ADPH. So the problem that appears now is that we finished up the Calvin cycle and the light reactions, but we've reached a bit of a problem. You need more ATP than you do NADP out of the light reactions, and the light reactions produce equimolar amounts. So for every molecule of NADPH, you get a molecule of ATP. So what's going to happen here is you're going to run out of ATP before, and you're not going to have enough NADPH. So if I make 18 ATP, that's going to give me 18 NADPH. At some point, I'm not going to have enough of something to keep the Calvin cycle running. So we've got a bit of a problem now. And that problem is that you're basically not going to have enough ATP out of the light reactions to drive the Calvin cycle. So think about this. You get 12 ATP out. That's not enough. You've got enough NADPH. 12 NADPH, 12 ATP. Where are you going to get the other ATP from? Okay, you can't bring them in from the mitochondria, so we've got a bit of a problem. I'm going to address that problem in our next and last video on photosynthesis. I'll see you next time.